So let's dive into our first topic and understand the photovoltaic effect. This is the key process that allows solar panels to convert sunlight into electrical energy. The photovoltaic effect occurs when photons, which are particles of light, hit the surface of a semiconductor material, such as silicon. When these photons interact with the silicon atoms, they transfer their energy to the electrons within the atoms. This added energy allows the electrons to break free from their bonds, creating an electrical current. This flow of electrons is then captured and directed into an electrical circuit, where it can be used as electricity. Silicon is commonly used in solar panels because of its unique properties as a semiconductor. It's able to absorb a wide range of light wavelengths, making it highly efficient at capturing energy from sunlight. Additionally, silicon is abundant and relatively inexpensive, making it a popular choice for solar panel manufacture. Now that we have a good understanding of the photovoltaic effect and how it allows solar panels to generate electricity, let's move on to our next topic and learn about the different types of solar cells. Alright, so now that we've covered the basics of the photovoltaic effect, let's discuss the different types of solar cells that are commonly used in solar panels. There are three main types: monocrystalline, polycrystalline, and thin film. Each of these types has its own unique characteristics, efficiencies, costs, and applications. First up, monocrystalline solar cells. These cells are made from a single high-purity silicon crystal, which gives them a uniform appearance and excellent efficiency. Because of their high efficiency, monocrystalline solar panels can produce more power in a smaller space compared to other types. However, they tend to be more expensive due to the manufacturing process and the high-quality materials used. Next, we have polycrystalline solar cells. Unlike monocrystalline cells, these are made from multiple silicon crystals that are melted together. This results in a less uniform appearance, with a distinctive blue hue and a somewhat lower efficiency. On the plus side, polycrystalline solar panels are generally less expensive than their monocrystalline counterparts, making them a popular choice for larger installations where space is not as much of a concern. Lastly, let's talk about thin film solar cells. These cells are made by depositing a thin layer of semiconductor material, such as amorphous silicon, cadmium telluride, or copper indium gallium selenide onto a substrate like glass or metal. Thin film solar panels are lightweight, flexible, and relatively inexpensive to produce. However, their efficiency is typically lower than that of monocrystalline or polycrystalline panels. This makes them more suitable for applications where aesthetics, weight, or flexibility are prioritized over efficiency and power output. So there you have it, an overview of the three main types of solar cells and their unique properties. Now, let's move on to our next topic and explore how solar panels are connected to form solar arrays. Now that we have a good understanding of the different types of solar cells, let's explore how solar panels are connected to create solar arrays. Connecting solar panels in series or parallel affects the overall power output and voltage of a solar energy system, and the choice between these configurations depends on the specific requirements of the installation. When solar panels are connected in series, the voltage of each panel adds up, while the current remains the same. This is particularly useful when you need to increase the overall voltage of your solar energy system. For example, to meet the input requirements of a specific inverter. In a series connection, it is important to ensure that all panels are of similar type and power rating to avoid imbalances and reduced performance. On the other hand, when solar panels are connected in parallel, the current of each panel adds up, while the voltage remains the same. This configuration is helpful when you want to increase the overall current of your solar energy system to handle higher power output. In a parallel connection, it's crucial to use panels with the same voltage rating to avoid potential issues with the system. In many cases, a combination of series and parallel connections is used to create an optimal balance between voltage and current while maximizing the power output of the solar array. This is known as a series parallel configuration and is commonly used in larger solar energy systems. So, to sum it up, connecting solar panels in series or parallel affects the overall power output and voltage of a solar energy system. By carefully considering the specific requirements of an installation and selecting the appropriate configuration, a solar array can be designed to deliver the desired performance. Now that we've explored this topic, let's move on to our next subject and study the role of inverters in solar power systems. Now that we've discussed solar arrays and how panels are connected, let's focus on the essential role of inverters in solar power systems. Inverters are responsible for converting the direct current electricity generated by solar panels into alternating current AC electricity that can be used in homes and businesses. This conversion is crucial because most household appliances and devices run on AC power. There are two main types of inverters used in solar power systems: string inverters and microinverters. Let's take a closer look at each of them. String inverters are the most common type of inverter used in residential and commercial solar installations. In a system with a string inverter, solar panels are connected in series to form a string, and then the strings are connected to the inverter. The inverter then converts the combined DC electricity from all the panels into usable AC power. While string inverters are generally more cost-effective, they have a downside. If one panel in the string underperforms due to shading, dirt, or other factors, the performance of the entire string can be affected. Microinverters, on the other hand, are installed directly on each solar panel. This means that the DC electricity generated by each panel is converted to AC power individually, before being combined with the output from other panels. This setup offers some advantages over string inverters, including improved efficiency and the ability to monitor the performance of individual panels. However, microinverters tend to be more expensive than string inverters, which can impact the overall cost of a solar power system. In summary, inverters play a crucial role in solar power systems by converting the DC electricity generated by solar panels into usable AC power for homes and businesses. The choice between string inverters and microinverters depends on factors such as system size, budget, and performance requirements. Now that we've covered the role of inverters, let's move on to our final topic and investigate the factors affecting solar panel efficiency and performance. Finally, let's discuss the factors that can affect solar panel efficiency and performance. Understanding these factors is important because it can help you optimize energy production in various conditions, ensuring that your solar power system is as effective as possible. The main factors we'll cover are temperature, angle of installation, and shading. First up, temperature. Solar panels are tested and rated at a standard temperature of 25 degrees Celsius or 77 degrees. However, in real-world conditions, temperatures can vary significantly, and this can impact the performance of your solar panels. Higher temperatures can actually cause a decrease in the efficiency of solar panels, as the electrical output decreases with rising temperatures. To mitigate this effect, it's important to ensure proper ventilation and cooling of the panels, particularly in hot climates. Next, let's consider the angle of installation. The angle at which solar panels are installed can greatly affect their energy production. Ideally, solar panels should be installed at an angle that is equal to the latitude of the location, as this will allow them to capture the maximum amount of sunlight throughout the year. However, this may not always be possible due to roof design or other constraints. In such cases, adjustable mounting systems can be used to change the angle of the panel seasonally, or even track the sun's movement throughout the day, maximizing energy production. Lastly, shading is another factor that can significantly impact solar panel performance. Even partial shading on a single panel can lead to reduced energy output for the entire system, particularly in the case of string inverters. To minimize the effects of shading, it's important to carefully plan the placement of your solar panels and keep them clear of obstructions such as trees, buildings, or other objects that could cast shadows on the panels. Additionally, using microinverters or power optimizers can help mitigate the impact of shading by allowing each panel to operate independently of the others. In conclusion, factors like temperature, angle of installation, and shading can significantly impact solar panel efficiency and performance. By understanding these factors and implementing strategies to optimize energy production, you can ensure that your solar power system is working as effectively as possible in various conditions. And with that, we've covered all the essential aspects of solar panel technology and how they work to generate clean, renewable energy for homes and businesses.